Today we'll be speaking about moving meshes and shape optimization in our QuickerSim CFD toolbox for MATLAB. But before we do that, there's a few things to discuss. So I just revised the toolbox, a few words about it. Then a little bit of theory how the meshes are handled in our toolbox is really important so that you get your grips properly, because it's basic algebra, you will see, but I just have to discuss, so give me 5 minutes. And after we do that, we just move to 3 cases that we prepared for you. That is simple mesh manipulation, so just playing around with the functions. And then we go to a really nice thing that's very often present in some biological departments, like peristaltic flows. And we conclude with aerodynamic shape optimization on the NACA 0012 airfoil. And after that, the Q&A session takes place. And if you have questions meanwhile, just do not hesitate to ask them on the chat, because our engineer Jacob is gonna help you with that. So let's continue to the introduction. So as you already know, we've created an app that works in MATLAB and solves CFD problems within MATLAB environment. Basically, it's a set of scripts. They read mesh, they manipulate it, they establish boundary conditions, solve Navier-Stokes equations, and all the family of problems. And that's basically a set of routines. It's written in MATLAB and C++, pre-compiled, so it works pretty fast in many cases. And what we do is CFD and heat transfer. And there's also a simple graphical user interface that lets you scroll through all those problems that are given there as samples. We deal with microfluidics over there, heat transfer, biomedical flows, some turbulence is already there. You can also do combinations, so there's a diffusion transferred and heat transferred, and aerodynamics, as I show you today, for basic cases. There's even some stuff for shape optimization that's for today, porous media, shallow water equations, for some research areas, really nice, and compressible invested solvers there as well. And when it comes to geometry and meshing, we strongly recommend Gmesh, because it's an open source software. It was created in France. It's still being updated, and we've even created a set for tutorials. So if you Google Gmesh tutorial, most likely our tutorials will come first. And now I just got some message, but it's okay. And after that, we can just move to some little bit of theory of how you can deal with meshes here. And the key question is why it's quite easy to manipulate mesh in CFD toolbox. It is simply because we work in MATLAB and we have direct access to the arrays that store the data, and mesh data storage in MATLAB is inspired by the thing that's already present in the MATLAB PDE toolbox. So there are 3 arrays, P, E, and T, that store the stuff, while P contains the node coordinates, X, Y, and Z, if we deal with 3 dimensions, and E and T are a little bit more complex. Basically, they speak about the topology and the finite elements and stuff, but they are totally not important for the things that I'm going to show today. P is the only one important. Another thing is the arbitrary Lagrangian Eulerian formulation for the problems. So basically, if you are not familiar to that, it's possible to solve continuum mechanics problems in the framework where mesh can also move with the reference frame, so that mesh has its own velocity, and it's simply included in the formulas. So you start moving meshes and this problem still can be solved mathematically. It's called ALE, arbitrary Lagrangian Eulerian. And the mesh deformation techniques. So you can obviously manipulate array T, and you can do that directly, but we also define some functions. First one is called Deform Mesh 2D, and it's gonna work for global deformations, where you will be able to fix some edges so that they don't move and other ones move with respect to them. You will also be able to perform some rotations against predefined axes. And the thing that's pretty useful is also the thing that's called radial basis function. So basically, it's going to work in a way that you will pinpoint a certain location in your mesh, and you will prescribe its displacement or its velocity or something like that. And obviously, the mesh has to be somehow smoothed. So you cannot just simply move one element, one node of the mesh. So the neighboring nodes need to move, and they are moved like by certain distance that is smaller than the direct, like the central displacement. And this basis function, its parameters, tell you how this motion is defined. I'll just explain that on the examples later on. You'll see. And okay, like without giving too much theory, because that's fair enough for today, I just want to show you how all these things work. Okay, just let's double check that I'm still here. Okay, yeah, just like there's some conversation here. Okay, good. So the very first mesh deformation basics webinar. So let's start about reading the mesh and viewing the case. Okay, maybe let's just clear that. And let's start. Let's just view the case. It's our lovely CFD example. It's the cylinder geometry in a channel. Just give it a second to load, because there's a new function for display, and it takes slightly longer. But simply a mesh inside, inside there's a hole, inlet, outflow, and top and bottom walls defined like number 10, 11, 12, and 13 is here. And we're just gonna simply deform that a little bit. So it's right in here. One thing that specific for our toolbox, we have to update it to second order, like there it was already explained. And for now, let's just play with arrays P. So you can see that P is 2 by n array, and it simply stores the coordinates. So you can do simple algebra. I assume that I want to just shrink the mesh by 15% in the x direction, and at the same time I want to expand it by 30 direction in the vertical, 30% in the vertical direction. And I also have to describe some certain reference point with respect to which we perform this deformation, and that's just like a linear transformation. That's just like a linear scale. P1 x that's x coordinate, P2 it's y coordinate. So we simply perform this piece of algebra, and without too much effort, you can see that it got slightly extended in here. It's slightly egg shape. It's not anymore round. So that's the simplest you can actually get. Well, we can do a little bit more of algebra in here, and let's assume that we still also want to rotate. Yeah, so just again, that's algebra 1, rotation matrix R. So it's cosine of the angle of rotation 30 degrees minus sine cosine, and we just perform matrix vector multiplication. And after that, okay, it's called P new. Okay, you can see that the thing is rotated right now. So yeah, that's fairly simple. So if you want to do the maths yourself, you have the direct access, and you can do whatever imagination tells you, affine transfer, whatever you wish. But there's much more into that, because obviously sometimes you want to have something that's more handy. And for this reason, we define the global deformation, deform mesh to D functions. And in this function, what we do is actually we start moving the boundaries of the objects. So as you've noticed, like the 13 was the circle inside, and 10, 11, and 12 were the side edges. So I will be moving the mesh in a way that's holding by the circle. And So that's, I define it here, the edges numbers, and I also, what I do is I define additional data for transformations. So actually this function can be also used for rotations. So this is the rotation axis. Those two parameters are x and y displacement, and the third one is the angle that I would like to rotate things. So then I call Deform Mesh and I visualize that. So let's just like have a look how it works here. And you can see that compared to the previous one, like the cylinder moved slightly to the x, negative x, and positive y. Yeah, and maybe we could try to twist it a little bit as well. So I would go like, it's in radians. How much is that? Let's do 0.3 as well. I'm not good at radians, but let's see. Obviously, the elements are becoming more skew, but you can see that the things start to be deformed. So like the circle now that turned to egg, now it's a little bit tilted. So that's how you can prescribe the motions here. And yeah, it starts at P nu, and if you just compare it to the previous one, maybe let's just make it like figure 3, and PT. Let's evaluate the selection. Okay, that's the previous one. And where's the, okay, and I want to do that, and okay, it disappeared. Figure 4. Display mesh P nu, P nu, like that. Oh yeah, so you can see the comparison in here. So yeah, that's pretty handy, especially like if you want to manipulate the motion of a stiff body inside the fluid. Okay, and the third thing I mentioned, those are the radial basis functions. And now the point is, like you will see that in the next example, they are really flexible. For now we just start with one point. So here I prescribe the coordinates of the point with respect to which I want to perform this slide transformation, and I also prescribe the value of the standard deviation of this Gauss curve that would simply say how far it reaches. And that's the displacement of the control point. So in the point picked at 0.5, 0.5, we will move it 1.2 in the positive vertical direction. And the way I use that, I just init this function. Pinit stores the previous geometry, and P stores the deformed one later on. And Tm is the transformation matrix. So that's simply like a linear transfer. So let's have a look. That's going to work pretty drastically, but the way it looks here, okay, obviously I have to display both. So the initial one is, back to our egg in here, and the new one works like that. The new one is here. Okay, so that's pretty intensive. But you can even see that slightly the side edges are deformed as well, because it has like a large radius of attraction for those points. So you can make like really strong manipulations in that. But it's going to be much more clear on the next problem why it's so useful. Because we want to, as I just repeat, we want to deform the mesh globally, and somehow it should be smooth as well. So yeah, just now we can move to the second problem. And the second problem is the peristaltic pipe. So as I told, it's common in this kind of motion. It's like biological motion, and the walls are contracted in here, as you can see, and these contractions, those contractions will be moving to the right, and they would try just to squeeze out the fluid. So yeah, that's how the problem works. So let's go to the Peristaltic Pipe webinar, and let's just scroll through the data through the script in here. So we read the mesh, we update it to the second order, and maybe let's already display. Let's just display the mesh. P new and P. Okay, yeah, so that's nothing special. That's just like a straight channel. But now I just prescribe the motion first, just give you a taste of how it looks. So I already, now that's the basic one. Let's go in here. I also defined fluid viscosity. I initialize the velocity field with 0.05 velocity, some inlet pressure. Here I give the parameters for the frequencies with which those peristaltic waves would move. That's some stuff for time stepping, because that's going to be a dynamic simulation. And here is the definition of the problem. So for tests, make it 200 time steps and radial basis functions. So it's a little bit longish. Now it's purely in numerical terms, no symbols. But the point is that there are four, as you remember, there are 4 points. Okay, not here in the presentation. Yeah. So first one, second one, third, and fourth, and each of them has its specific radius of influence. So it's actually like a 3x4 matrix, and you can see that's the standard deviation. That's the location of the x point. That simply changes linearly in time, and y is 0 or 0.01. And again, y is like 0 or 0.01, so it's bottom and top. And that's a simple cutoff for x. If it's it is longer than 0.06, it drops. So that's simply a thing that guarantees the periodicity of the first one and the second point. Here is again the formation of the mesh with radial basis functions. So those displacements are also given in terms of harmonic functions. So we have sine of the coordinates that appear like x coordinates. We also store the meshes, p alt and pk. And yet another important thing, since this is a dynamic simulation, we will have to store the velocity of the mesh itself. So we will subtract the positions of the edges of the nodes, the new ones and the old ones, divided by time step. And this velocity Vm will be important in the Navier-Stokes formulation later on. So you will see we solve the problem of u minus Vm. But first, let's simply have a look about how all those things work. And where did I finish? I read it. Let me just initialize it like that and hope that the display is correct. So we evaluate the selection. Okay, can I make it like a larger one? Okay, it's small one. Sorry for that. I thought that it would redo work on the first one. Okay, maybe we can just sort of like kill that or just stop it. It's really hard to stop it sometimes. Okay, it's almost finished. Just give me 4 more seconds and you will see that we can just redo that with nice. Yeah, okay, so now the picture is fine. Like maybe again, let's redo the thing. Maybe just try to do it on 50 steps and the figure might be good this time. Evaluate selection. Yeah, okay, good. Now you can see those guys moving, like this one and this one in full resolution. So yeah, this is the mesh motion. And on top of that, we want to take care of the fluid flow simulation. So now the things are pretty straightforward if you are already familiar with our toolbox. And that's already coded in here. Let's just unlock Navier-Stokes, uncomment that. Okay, maybe I just comment that in here. And that's the figure. And now this is just for visualization purposes. So yeah, maybe let's do like only 50 time steps. Okay, let's just put it to yeah, like make it neat and make it, or maybe just like 20, because it's like that. I'm just doing that on my laptop. And yeah, the simulation just begins. Things get initialized, and again, yeah, okay, now it works fine. So you can see step by step show up, and okay, the simulation is underway, and yeah, it's here. So you can see that velocity is positive on the right and negative on the left, so it's sort of squeezed out to the sides. And you can also see the pressure waves. So like there's a positive pressure on the right and some sort of under pressure in here, because still the flow goes a little bit from the initial state to the right. So yeah, that's how it works in our toolbox. And there is like obviously no sense to iterate that for longer times, and just what? Let's check if this converged. Okay, it's 14 steps. Let's just like try to kill it. Okay. Yes. So it's yeah, it was pretty fast, and I can just show you the video how it works in full scale. Okay, let's just yeah. So that's when the simulation is performed for a little bit longer time. It gets cyclic, and you can see the velocity in the flow and the mesh deformations and the pressure waves, and it's really nice. Here that's a slightly different case actually, because it also involves non-Newtonian fluid rheology, so it gets like more viscous inside, but yeah, that's just yet another function, and that works pretty well in the toolbox. You can see that the change of the topology of the mesh is pretty significant in here, and stuff like that. Okay, so that's the second case for today, and now let's move to the pinnacle. And the third case is the aerodynamic optimization, automatic shape optimization, that's going to be performed using the optimization toolbox and our solver and mesh deformations. So the problem is the following. We have an airfoil, NACA 012 as basis, for the flow that is at 5 degrees angles of attack. And like, since the flow is like non-symmetric with respect to the airfoil, there's obviously there's always going to be drag for a viscous flow, but there's also lift. And what we want to do, we want to modify the shape of the trailing edge so that for this fixed angle of attack, we would maximize the lift to the drag ratio. And the question is, how much should we deform that? And yeah, that's pretty obvious that we can do it by a method of trial and error, but we have the optimization tools available for us. So just to give you an impression how relatively doesn't require much work. If you attended the previous webinar, or if you are a little bit familiar with our toolbox, so you already know the NACA 012 flow. So the whole solver that solves the flow is wrapped as a function that's called CFD solver. But the solver itself reads the mesh, it extrudes the boundary layer. Okay, actually we can show that again. And yeah, okay, maybe let's clear it first. Okay, this should work without referring to the function. We evaluate. the selection and display mesh 2D P and T. Are you here? It's a subplot. Oh, sorry. Okay, again. Yeah, now that's better. And let's have a look at that. Obviously, like, we need much space for the aerodynamic flows. Sorry, it's not smooth at the leading edge, but it's just for demonstration purposes. So you can see like the boundary layer generated here. And we will be changing like the end in here. And now we define the radial basis function at the end of our airfoil using this few lines of code. Then we update the mesh. We also define the fluid as air. We initialize everything. For the turbulence model, we also have to compute the wall distance. We define the angle of attack, inlet velocity, the inflow velocity, and this part of the solver simply takes care of the fluid flow convergence. So we have to find turbulent viscosity. Here there's some under relaxation. We just assemble the Navier-Stokes matrix and impose boundary conditions. Here just plotting some residuals and solving equations. And then lots of post-processing is just closed, just a waste of time. But then we just compute the forces, because simply forces are our objective function. So the ratio of actually lift to drag coefficient is our function that we want to want to minimize. The thing minimizes it, so we just have to change the sign because we want to get maximum L over D. We also save the data and keep it. So yeah, that's the regular solver. I can just demonstrate you how the optimization loop works. And the parameter alpha is simply the vertical displacement of the trailing edge. That's called trailing edge. And this function, f, min, b, and d, is the function that comes from MATLAB optimization toolbox. Obviously, you can write your own functions if you do not have the access to this toolbox, but that's a pretty standard toolbox. And you can see that it gets a handle to our function that's called CFD solver, because all the solver is wrapped into that. And those are the lower and upper bounds. So somehow it should be just alpha min and alpha max put in here. And that's a set of options. I say that I just want to evaluate this function here only once, because I just do not want to spend too much time on calculations. I will just show you that it indeed works, and then I will just show you how what are the results that we get just after a few evaluations of that. So yeah, I just called the external function, this piece of code, but the things that operate over there are pretty straightforward and should already be familiar to you. So here's going to be convergence. Let's check. Okay, I can see there's some conversations being carried out. Great to see that you guys are interested. And let's just see how it converges. Okay, 5 steps. And yeah, it continues. 6. What's the size of the mesh? It's not too large. It's, as you've seen, like it could be more smooth, but as I tell, it's just for demonstration purposes, and I'm just using my old laptop with an i5 processor. So like if you have new equipment, it's gonna work much better. But anyway, for doing CFD with turbulence models, it's fair enough. And let's see the residuals. Is it a new mesh or an old one? I wonder if we can visualize that already. Yes, okay, so as you can see that this is the first guess of the optimization loop. It deformed edge quite significantly to the bottom. and the simulation is being carried out in this geometry for now. Still, let's give it a few seconds, and we'll see the level of residuals here. Keeps on dropping. What's the bound I've chosen? Probably 10 to minus 6. Yeah, it's 10 to minus 6. Okay, so it's almost finished. Okay, so yeah, that's what we've got after the simulation. So the design parameter, that means the Y displacement, is negative 0.85. And the lift to drag is 8.992. Okay, somehow, okay, probably that option over there wasn't exactly the number of function run. It was might be something a little bit different. That's why it started for the second time. But like, okay, let's check the geometry. I don't know. Okay, let's okay, let's just close it because it makes no sense. I just have to kill the process now. Okay, yep, that's the thing in here. And as I tell you, like the intermediate data is being saved to some files. It's in today's webinar folder, and yeah, so that's those are the files that are being created. And yeah, so you can go back to those results and play around, watch them. But anyway, I want to show you the final outcome. And the final outcome is the following. Maybe just first in a full screen. Okay, no, it's bad. Maybe just like mesh deformation first. So the way it would work is the following. First it's straight, then it goes to the bottom, goes a little bit higher, strong to the bottom, in the between, and now the corrections are minor. Like here, those are barely visible. Like after, like first 5 matter, then like these are really small. And yeah, that's how velocity would change throughout all those simulations. Here, like actually there would be a separation. It's too strong, and this even the simulation doesn't make much sense if you look into the details. But that's how the solver performs. And again, the changes are minor. And let's maybe still look at the pressures as well. So the pressure is here. That's standard straight flow. I mean, straight profile. And yeah, like sorry, the scale is pretty different, so that's why the colors change. Okay, it's automatic choice of scale. We could just replot that, but you can see that it stabilizes. And when you look at the plot of the convergence functions, it's going to be like that. So that's the design parameter. So that's the value of alpha of the deformation, and it just like goes between 0 and minus 0.15. And that's the L to D ratio on the right axis. And they simply like change. You can see how during the simulation the design parameter is just changed up and down. Yeah, and like here it's pretty okay. Like it's almost constant. You can see, yeah, design parameter and lift to drag, and it's more than 9. It's like 9.16 or so, maybe not 16. But that's how the loop performs. And like there's a movie online that also explains that. I don't want to download VLC. It just basically explains what is happening in the simulation. So we could just check it out online. And yeah, maybe it's a little bit too fast. We're just going to shorten that. And so we can get back to these results as well. So yeah, so that's the outcome. And yeah, just to sum up, it's like for me that's relatively intuitive how to manipulate this mesh. It's just algebra, and you just can resort to a few functions. If you want to get some details, further details on that, there's actually a tutorial whose name is Shape Optimization, but it's more about mesh deformation. Like the shape optimization was supposed to be second part. But over there, again, we explain in detail how all those things perform, radial basis functions, and in 3D, and the stiff deformations in 2D in here. So this one's pretty strong one. So it's all there. You can play around with it. You can even export the geometries to STL format, like 3D printing and whatever you wish. Visualize that. You just can go through movie that is related to tutorial 6 to repeat all the things that I explained in more detail. So yeah, so thanks for that for now, and I hope that you like that. And now there's the time for questions. And like before we move to questions, like the ones who are not interested, thank you very much for your attention. Just download and subscribe to our website, comment it, and like really we would appreciate your feedback on that, and what we can do in future, what we can do better. And hey, let's move to questions. I will see them. Let's just make it like 20 minutes. Okay. Harris, I can see that Harris asks if you are applying any smoothing. Well, and Jacob replies that it would be difficult using our software, but I don't know if it refers to smoothing, because I can have actually have a few ideas about smoothing so far. Like it's pretty regular procedure, and you can implement pretty nice finite element formulations for smoothing, because you could consider the nodes being like in a truss. I mean, okay. So I just replied to Harris is that I have a few ideas about that, and yeah, but it's like a little bit more advanced function, and like it's not there yet. That's a really good suggestion, and it's also related. It's also related to other problems, like to extrusion of boundary layers. So basically, we are working on that. Maybe it's not going to be present in the nearest release. I mean, some strong corrections will be present, but like the one that it's smoothing for mesh, it's not present yet. Okay. I wonder if there are any other questions from your side? How to check whether there's a deformity in mesh, such as high skewness? Well, there are a few ideas. I think that checking skewness should be pretty straightforward. The more important thing would be checking for the negative volumes, and there is a function that checks that corrects that occurs in three dimensions, and yeah, it's already there, and it can fix that to some extent. Well, clearly it's not meant for I mean, it can do really large deformations if you just pay attention. In general, like many solvers for really advanced meshing and like mesh deformations, what they would simply do, they would do remeshing. So like you could do remeshing using PDE Toolbox. We are also preparing a tutorial on that, and yeah, that's one of the options if you have really strong deformations. Yeah, and yeah, like meshing is the hard part all the time. Okay, I wonder if there are any other issues coming up. Somebody's still, I can see, writing a question. Okay, let's just put it like that. Okay, maybe this, and can I see the chat in here? Okay, not. Okay, so things like that. How to check, is geometry extraction possible? Yes, yes it is. Okay. Yeah, okay. Jacob asked, can I tell everybody how to access materials from the webinar? Okay. First of all, most materials are already available. You just go to QuickerSim.com, and once you download our toolbox and you install it into MATLAB, which is already done in my case, clearly, if you go to the main, if you just launch the toolbox, you will see the app in here, and that's a scroller through the tutorials. So the first tutorial was based on the mesh generation in Gmesh, tutorial number 10. So you can open an M file and a PDF file, and what will show up is tutorial 10 that shows the functions that work on the mesh in here. And you will also have the access to the script and the cylinder geometry in here. The same holds for the tutorial on the shape optimization. And tutorial on the shape optimization is number 22. So there's no number here. Maybe you should just put the number, but it's called automatic shape optimization and the solver. So the instruction is here in terms of a PDF file. And tutorial 22, that's the text in here. You just have to split it into two pieces, like CFD solver here and just like copy the first thing here. But what I actually showed you today was exactly the tutorial number 22. And the Peristaltic Pipe is not released yet. Okay, that's the landing page. I'm back here. So it's like it's gonna show up sometime in May. There's just like a long queue of like demonstration material in this case. And yeah, that's all. For meshing, we do not do mapped meshing. Apparently mapped meshing, I mean, now I'm not 100% certain. We do what Gmesh does. As I mentioned at the very beginning, we strongly recommend just using Gmesh in here. So like we get meshes from there, and sometimes we just smooth them a little bit. So you just go to gmesh.info and you download the software and use things over there. And yeah, grid size is limited by RAM memory, like for 16 gigabytes. In the newest release, it should be able to handle like 500,000 nodes easily. Yeah, it's like 6 gigabytes, 16 gigabytes of RAM. And yeah, we're still like working on that. Obviously, if you're like a researcher working on a stronger workstation, just going to 1 million, it's not a problem. And yeah, our ambition is to be just able to handle like 1 million on a shared memory architecture, because we do not plan to go to sort of like multi-processor and like, how do you call it, disjoint memory, so that you have to use MPI. That's a totally different story then, and that's a heavier weight solver. And yeah, so it should be like nodes for 16 gigabytes. Probably it can get even better for some cases. It strongly depends if you use obviously 2D or 3D. Well, depends what you mean by large, Harris. It's not a large solver. I mean, there are plenty large solvers on the market, and they all come at a price. Like OpenFOAM is great, but then you struggle to learn it. We also use OpenFOAM in an industrial project. Obviously, there are many commercial solvers, but simply we just want to be like a lightweight solver. I mean, yeah, like just reaching 1 million nodes for us would be a nice target, and lots of engineers and researchers benefit from that. It's rather the simplicity and the speed that we aim for than just the heavyweight stuff. Like in the future, maybe if things go well. But the point is that we simply do not want to compete directly with other solvers, because that just makes no sense. There are many good solvers on the market. Yeah, like it was also using RBF for large meshes. It gets computationally expensive, or employing any data reduction technique. Well, honestly, I don't know. Like I haven't written this piece of code myself. I would just have to talk to the engineers, and we would let you know. Okay. So, like, are there any other questions? Like, how many people are there? There are 22 participants still present. And I'll just ask questions. Okay, I just maybe reply to Harris. Okay. What kind of turbulence model does this tool cover in general? So now it covers like basic 0 and 1 equation models, because like two equation models turned out to be like pretty challenging, and that's reserved for like middle year release. So the thing that's called there, it's KL, it's CITM, and there's something that's called Chen Xu and stuff, and yeah, and also like this KL works really great. People are used to K epsilon, but for simple aerodynamic cases, you would see that it performs well. And yeah, actually, guys also implemented Spallard Almaras like during sort of like a tea break stuff. Maybe like it should be present in like the mid-year release as well. But yeah, as Jacob has it. But for now, if you just want to check the validation, you can go to our website, news, and you will see the validation using apparently CITM model. If I'm yeah, constant density turbulence model for pretty small meshes, for Reynolds number 50,000 to 400,000. It was validated with some really nice old NASA results, and it works really well. Okay. Yeah, exactly. Plans, no. SST. Well, yeah, like SST, that depends. Because that's not the top priority in case. Like K epsilon and K omega is top, and X and K is top priority now. And like Sparmals apparently well. Sure. Okay, John Sebastian, thanks a lot. And thank you very much, everybody.